Welcome everyone, and here's your weekly video going through the video assignments that were submitted this week. So exercise 1 from chapter 6 and 7 says, pick one of the poor sampling designs, describe it and how it is biased, right? So the intent here, I'm not going to do the writing because there's actually multiple answers, but is to go back to video 6-2 and identify some of these, right? So there's 4 of them to pick from, and then why are they biased? So convenience sample, you're just selecting those near you, and so there's other people that are not potentially being selected that you might want information from. Voluntary response would be the idea of sending out a survey, right? And then only those that are motivated to send a response do. Purposive sampling is you actually picking, here are all the people. I want a response from X, Y, and Z people. And then snowball is, you give it to 2 friends and then you give them some samples to share or something like that, and then they just continue to spread it among their own networks, right? So that's, again, you're selecting specific networks, not the general people from the general populace as a whole, or the population that's identified. So that was the intent with that exercise. Number 2, 3 principles of experimental design. Well, first is randomize, right? You want to make sure to randomize everything as much as possible just to make sure that you're involving different elements and eliminating bias, right? Next thing is you want to control your lurking variable. Now this, you might be familiar with confounding variable from earlier in the course. They're very similar. Lurking variable is something that you're aware of in the experiment that could affect the results, right? So you want to try and control that via a control group or a different type of design, right? And then the last one is you want a large sample size. Generally, if you get a large enough sample size, I'm talking thousands or tens or hundreds of thousands, that's going to dominate everything, and so that will be sufficiently large to control lurking variables. And if it's done randomly, then you're going to have a very good experiment. All right, number 3, draw a block design experiment. Specify your blocks. And so you can pick different things. One easy one might be, you have your population of, I don't know, say college students, and you select, 10,000 of them, and then you partition them into 2 groups, say male and female. So you're blocking by sex, so these are your blocks. So males and females, okay. So I'm going to just say randomly select, and in that 10,000 group, you might have an equal split of males and females, maybe not. Let's just assume you don't. So I'm going to do 4, 5, 0, 0, and I'll do 5, 5, 0, 0. I don't know, just to see something else. And then maybe you're testing the efficacy of a new sports drink. I don't know. So then you give them, your control, which might be a Gatorade control, and then you give treatment, which might be the new type of sports drink, and then what you're measuring. So in each of these you measure, say, time to recovery after an intense workout. Okay, so I'll say experiment, and then you can, after that, I should put that maybe in its own box, and then you measure what you need to measure. Okay, and very similar things. So you do control, and treatment, and then you do your experiment, and then you measure for the other group too. So you're doing the same experiment twice with same experiment with each of the different groups that you blocked based on. And again, these this block, so maybe you block based on some lurking variable. So you're thinking that sex could be influencing time to recovery, perhaps. And so that's why you're separating it out. Maybe you want to separate based on a different characteristic, right? Hair color. I don't know why that would ever affect anything, but maybe you want to do that, right? Or sensitivity to light. I don't know. So you might have to partition into different groups based on something that you know could affect the results. So chapter 6 and 7, that is that video assignment, right? And so we'll move on and go into the next one here now. Chapter 9, probability, and that might strike fear into some of you, but I promise this course we do very light probability. So we will get through it and we will persevere. First exercise, it says identify the 4 rules of probability. So first, all probabilities are between 0 and 1, right? They're a percentage, or you can rewrite them as a percentage, right? But they should all be decimals between 0 and 1. Next thing is all, or I should say, the sum of all probabilities. Some of the probabilities of all events in a sample space must sum to, or must be 1, I should say, must be 1. So if you're considering what's the chance that it rains, what's the chance that it snows, what's the chance that it's sunny outside, what's the chance that it's cloudy outside. If you look at, say, all the weather, or all the different possibilities for the weather, if you look at that for a certain geographical area, all those probabilities must always add to 1. Okay? For example. Third, the sum, or the sum of, let me get my language right, actually. So we're going to say this is dealing with the disjoint property. So disjoint events, the probability of disjoint events. Here we go. The probability of disjoint events can be added. Probabilities, plural. Oof. Grammar. Disjoint events may be added. So what's the probability that a shirt is blue and probability that a shirt is green? Those may not be disjoint events, because you can have a single shirt, depending on the type of shirt we're talking about, that is blue and green, right? But if we looked at whether the shirt is a medium or a large, right? In size, right? You can't have a shirt that is both medium and large, so you can look at adding those probabilities. Okay? And the last rule is the complement rule. So the sum of, I'm going to phrase it differently and I'll write it. So the sum of complementary events, the sum of probabilities of complementary events, complementary events is 1. Okay. Another way to say that same thing is if you have P of A, so that's an event, and you look at the complement, that's 1. Or if you rearrange this, right, move, say, P of A here, I'm going to move this to the other side, right? Mathematically, if I move it to the other side of the equation, you just get probability of the complement is 1 minus probability of the event, which is what was said in the video. So it's just another way to reframe that. Okay, and this rule will be very, very handy this week and next week as we're working with probabilities. All right, on to exercise 2, which is our last one, and it's a bit of a beast. So it has a number cube, 6 sides on it. There's 3 sides out of a 1, 2 sides out of a 2, and 1 side is a 3. And this number cube is rolled once. So the sample space is the possible outcomes, right? And so what could we get when we roll this cube? Okay, a 1, a 2, or a 3. That's all that the cube would have on it. Okay, and a sample space, we always have to enclose it in braces, and if you want to write like S is equal to, that would be even better. Okay, so just what are the outcomes of the experiment, or this random thing that we're doing? Okay, so our outcomes are 1, 2, and 3. And what's the chance of getting those? What's the probability, right? So in each of these are going to be fractions, and there are 6 total sides. So our denominator is the total number of possible outcomes, right? So there are 6 total sides of the cube. How many of them are a 1? Let's see, that is 3 sides have a 1 on them. So that'd be 3 out of 6, okay? If you want to simplify these, feel free. Number 2, how many sides have a 2? 2 of them, right? And then one side has a 3. Okay, there we go. So that's our probability model. Probability model is just a listing of all the probabilities for the given events. A is rolling a prime number. Okay, prime numbers are numbers that have a factor of themselves and 1. Okay, so therefore 1 is not prime, so this is just 2 and 3. So probability of A is, if you wanted to write it as probability of the events like 2 and 3, you sure could. Either notation is fine. And so then we would just say, okay, well, we're saying, okay, well, on our number cube, how many sides are a 1 or a 2 or a 3? Well, that'd be 3 of them, right? And so if you want to simplify that, again, feel free. Now, when I say probability statement, okay, this is super important. This is practicing some notation and showing our work to a degree. That would be P of A. Okay, so make sure to get that in every probability that you write needs that with it. Okay, part D, discuss what A complement means in this context and find the probability of this event. So A complement is rolling, okay, if A is rolling a prime number, it'd be rolling a non-prime number. Okay, so then, so then you say, oh, the only non-prime number is 1, and you can say it's 3 out of 6. Yes, I get it, but the intent is for you to do the complement formula. A complement would be 1 minus P of A, and luckily we calculated P of A above, so this is 1 minus 3 over 6, and then remembering your fraction arithmetic would give you 3 out of 6, or again, 1/2. Okay? So again, most of the probabilities that we're going to do this week are going to be fairly standard around some of these rules that we've seen here, right? The later weeks will extend it a little bit, but again, the math that we're doing is not going to be terribly complex. All right. So next up, we'll overview the videos or the activities for the week, and then we'll be on our way.